And can you hear me? That's great. And so thank you so much for being patient, and sorry for the mess, but we are ready to start. All right, so small recap. The scope of the aim of today is to have a look at the Irene package to compute persistent homology. Irene is a package on Julia. For those of you who are new to Julia, like me, I promise I'll be slow and I'll explain every step along the way. All right, so if you want to follow the computations from the PDF, thank you, Oliver, from the PDF advertising the course, you should be able to follow a link to my Google Drive to download all the files needed for today's lesson. Now, I have a disclaimer before I start, and the disclaimer is that the new version of Julia doesn't talk well with the Irene package, in particular with the plotting function of the Irene package. That's why today I'm using my old laptop and using an old version of Julia, in Julia 1.4.1, because it was more convenient for the purpose of the class to, use plotting functions built in Irene just to show what we are computing and to try and give an interpretation of what we are computing. But no worries, because I'll show you how to save all the data we are going to compute, and once you know how to save it, you can either plot it and analyze it using different plotting functions in Julia, or perhaps with any other language you are more familiar with, Python or whatever. Anyways, let's start. I'm starting by running the packages, by importing the packages I'm going to need. And Julia, for those of you that are not familiar with it, has this small drawback, namely the first time that it has to do something, it's quite slow. So the first time that it's loading a package, or the first time that it's using a function in a package, it is quite slow. Apart from this, initial drawback, this initial time taken, it's a very fast programming language, and it's been increasingly used by mathematicians and by data scientists. So probably many people in the audience will be more familiar with Julia than I am. Anyways, we are done with that, and we loaded all the packages we need today. Now, as a first example, I want to recompute the persistent homology of the same point cloud we used a week ago in class. Okay, just as a sanity check to see that in class we did the same thing and we were correct, and that and to understand a little bit what are the main functions of Irene we're going to use. So I'm loading the point cloud using class, and you can see here it's 1, 2, 3, 4, 5, 6, a bunch of points, okay? 1, 2, 3, 4, 5, 6 points, and these are the coordinates. We have the origin, and then the point 0, 1, 1, 0, 1, 1, 2, 1, and 4, 1, okay? I can plot it using this built-in function in Irene that you probably won't be able to use if you want to use a updated version of Julia, but nevertheless, let's see it. It's the function we are going to use today. Again, first time I'm calling a function, it's going to take a little bit of time, even if it's a very simple point cloud to plot, right? Just 6 points in R2. And here they are. Now, this built-in function in Irene works very well when you have very complicated point clouds. In this example, it doesn't quite do the job, okay? Because the point cloud is very small and the plot is quite sparse. So, just for this example, I'm going to use a different function, still using the same plotting package, Plotly, that again with the new version of Julian doesn't really work. But anyways, different packages have a similar syntax, so it's still useful to have. And here it is, okay, exactly the same point cloud we constructed, of which we computed persistent homology a week ago. And just as a recap, I'm I copied the summary of the filtration of the complexes we constructed from the point cloud using the Vittori's Frisp filtration. Okay, so just so we remember what we did last time, we noticed that while we are increasing the time parameter t to construct our simple shell complexes, nothing happens until time equal 1, because that's the smallest pairwise distances in our point cloud. At time 1, we noticed that we were adding these 5 one simplices, and we were creating a one loop. So our first homology H1 at this point had dimension 1, our Betty number was 1, we had a unique loop in the simple shell complex. Then nothing happens until t equal square root of 2. At this point we are adding a bunch of new one simplices and new two simplices. And what we are doing is basically we are closing this loop without creating any two-dimensional hole, because any void, because the only possibility for a void was to for it to be contained, enclosed by this bunch of simplices, but we are also adding a three-dimensional simplex to fill the hole. Again, following the definition of Vittori's Frisp filtration. Again, nothing happens anymore until time equal 2, where finally we are closing the attaching the last point. Okay. So we are getting something that's finally totally connected and with no holes. Okay. Now let's see what Irene does and what Irene tells us. This is the main function. So we want to compute the persistent homology of my object point cloud. I want to check if I have homology up to dimension 2. Okay, so with maxdim, with this parameter maxdim, I can tell Irene to check to compute homology up to the dimension I'm interested in. Throughout all of this lecture, is going to be maxdim is going to be either equal to 1 or 2. As I said last time, in this course we are not really interested in higher dimensional features. And then I'm telling Irene that I need to consider my input object as a point cloud. Okay, there are other things you can do with Irene. You can feed Irene distance matrices or directly simple shell complexes, and according on the input data you need to choose different models, and the filtration used by Irene is going to be different. Again, for this lecture, we are only interested, for us, data is just point cloud. So data means a point cloud, a bunch of points in sum are n, and n is going to be equal to either 2 or 3 throughout this lecture. And so for us, the model is always going to be PC point cloud. Okay? All right, let's compute it. Again, it's the first time I'm calling this function, so it might take a bit, even if it's a very simple computation. You'll see later on that I'm going to compute the persistent homology of point clouds with much more points, and it's going to take fractions of seconds. Okay, this is just because it's the first time that I called the function. Okay, and now I want to visualize the result. You remember last time from the construction of the filtration of simple shell complexes, we looked at when different topological features appeared and died, and with this information we constructed the persistent barcode. Okay, and now I can plot it. Actually, let me, again, this is a built-in function in Irene, so you won't be able to use it unless you don't rely on an old version of Julia. But anyways, let's see what we got here. Okay, so I'm asking Irene to plot the persistent features, the persistent barcode, in all the dimensions I computed, so from 0 to 2. I can also restrict to a single dimension. Of course, to any dimension that I compute. In dimension 2, we didn't find any topological feature. Okay, so this is the summary of the topological summary of my point cloud. And again, this agrees with what we computed last time. We saw that we start with 6 zero-dimensional features corresponding to the 6 connected components in my point cloud, so the 6 different points I was considering. At time 1, 5 of these points merge into a single connected component, and I'm left with 2, and they're finally all united at time equal 2. Okay, everything is connected. I have a unique thing. For what concerns first homology, we noticed that we were creating a hole at time equal 2, and that this one-dimensional hole was filled at time equal square root of 2. And again, this is what we see here in our persistent diagram. We might be interested in looking, having a different visualization of our persistent homology, and we might prefer to look at the persistent diagram, and we can plot it as it follows. Again, this is perhaps a too simple example for the functions built in Irene. I'm plotting the persistent diagram in dimension 1. As we know, we have a unique feature. This is represented by this single dot with coordinates 1 square root of 2. Okay, 1 is the birth time, x coordinate is the birth time, y coordinate is the death time, and that's square root of 2. All right. Now, I told you that I was going to show you how to save and plot, more in general, print, let's say, the results of our computations. Let's start by, actually, before we do that, sorry. Before we do that, one thing we didn't really discuss last time in class is how to interpret geometrically the topological features that persistent homology is finding. Okay, so we recognize while constructing our filtration of simple complexes that there was a single first homology class, a single one-dimensional loop appearing at some point in the filtration and dying at some other point in the filtration. Okay, we might be interested to understand geometrically, to interpret geometrically this one-dimensional feature. In other words, we might be interested in finding a cycle, a one-dimensional cycle. Remember that a cycle is a formal sum or a set, in our context, since we are only using Z2 coefficients, a set of one simplices without boundary. Okay? Remember, we defined what the boundary of a chain is, what the boundary of a simplex is, and what the boundary of a chain, so the boundary of a formal sum of simplices is. We call cycles those chains, those sums of simplices that have no boundary. So we might be interested in finding a cycle representing our one-dimensional feature, okay? And Irene can do that. By using by recording the information of one specific generator for each homology feature computed using persistent. Now, I should say here that cycle generating homology classes are by no means unique, okay? And Irene makes some choice. Irene picks one specific generator for each homology class, and this choice is not necessarily the best one, definitely not the only one, and might not be the one you were hoping for. But either way, it can give you a way to interpret geometrically the feature computed algebraically by Irene. We can use this built-in function of Irene to plot the point cloud together with one cycle representing the homological feature I'm interested in. And the way let me explain that, even if, again, plotting functions cannot be used in newer versions of Irene. Anyways, the syntax of this function is as follows. It takes as input, of course, the persistent homology, so the entire dictionary outputted by Irene, and then you fix a dimension you're interested in. In our case, dimension 1 is really the only interesting one in this example, and then you fix the index of the homology class you want to plot a representative of. Okay, this class is just the index. In this case, I have a unique homology class in dimension 1. Okay, if I had more than that, I would need to specify the index, and this is called class. Okay, in our case, not much choice, and here again is not visualization in this small example is not great, but hopefully you can appreciate that here I have my point cloud, and this shows one possible cycle representing my homology class. This is a very simple example, so the cycle picked by Irene is exactly what we're expecting. Okay, so the sum of one simplices drawing the one-dimensional world. Okay, any questions so far? All right. Now you can output the barcode in each of the dimensions you computed homology in, and this is the barcode is outputted as an array of dimension m times 2, where m, in this case 6, is the number of different homology features in that dimension given as input, and 2 is just because for each feature Irene is giving you birth time and death time. Okay, in this case we have, as we know, 6 zero-dimensional features. They all appear at time 0. They correspond to the 6 distinct points in my point cloud, and then we have 4 of them dying at time 1. That's when they merge with, that's when the 5 points merge into a unique connected component, and then a 5th zero-dimensional feature dies at time 2, when everything becomes a unique connected component, and the last one never dies. Okay, Irene records that as dies at infinity. Okay, from that point on I have a unique connected component. It's not going to disappear. Once you have this array as an output, you might decide to save it as a text file, for example, and we can do that just by using this function write DLM. This is a function contained in the delimited files package. Okay, and this works in any version of Julia, so this is definitely something you can use so that you can then later on analyze your results. And in the same way, you can output, instead of plot, you can output each representative cycles by using the function class2rep. Again, the input is pH, then we choose the dimension we're interested in, and then we specify the index of the class we want to the index of the class we want to find a cycle of. And I should say the index is the position of the homology class in the barcode, in the corresponding barcode, okay? And here it is, okay? Now, this function outputs the cycle representing this homological feature in the following way. We have an array of dimension m times n, where m, in this case 2, is 1 plus the dimension of the feature, and n, in this case 4, is the number of simplices, is the number of simplices involved in the cycle. So we should read this output as telling us that the cycle is formed by the simplex, the one simplex spanned by the second and fourth vertices in my point cloud. Then we have the cycle spanned by the third and fourth vertices, and so on. Okay, so we have the edge spanned by 2, 4, the edge spanned by 3, 4, the edge spanned by 1, 3, and 1, 2. Let's check that this corresponds to our plot. So this is the point number 1. We have the edge 1, 3. And here it is, 1, 3. Then we have the edge number 1, 2, 2, 4, and 4, 3. Okay? So 2, 4, 4, 3, 1, 3, and 1, 2. Okay? Similarly, for example, we might ask to output us the class representative of the fourth homology class in dimension 0, and this is trivially given by sum of the points, okay? The number 4 and 6, okay? That this correspond to the one of the mergings happening in the filtration. Any question here? Okay. Now let's try and see something slightly more interesting, okay? Now, I want to be able to show you some two-dimensional feature, okay? Because last time we didn't really do that. It's hard with drawing, so let's use computations to try and see what, two-dimensional features can tell us about the data. To do that, let me produce a new point cloud. This is going to be made up by 100 points in R3. I can do that by just randomly generating these points using the round function of Julia. And here it is, okay? I can plot this point cloud. Now the built-in function in Irene makes a much better job because this point cloud is slightly more complicated, so the visualization is much nicer. Okay, these are just 100 randomly generated points in R3. Let me say before we compute pH, of course we shouldn't expect to see some meaningful topological feature in this case, right? Because we are talking about random data, so kind of by definition, or not by definition, but we shouldn't expect to see anything, meaningful. Nevertheless, we will see one-dimensional homology class and two-dimensional homology class, and we will be able to plot things and to have a little bit of visualization of what's happening, okay? So let's compute Irene. You see, it took like a small fraction of a second, even if the point cloud is much more complicated than before, and even if we are still computing up to dimension 2 as well. Let's plot the barcode, and in dimension 2, and we see that finally we have something going on. Okay, the filtration produced by our point cloud is giving us some two-dimensional feature. Now, we shouldn't expect, again, these features to be very meaningful because we are talking about random data, but nevertheless we can see something, okay? Let me also plot the persistent diagram, because it's easier in the persistent diagram to find out the class, the index of each of these homology classes, okay? Remember that as it for persistent barcodes, the length of the bar encodes the persistent of the homology class, so how long it stays in the filtration, so likely its importance, how much it's meaningful. The same thing is true in a persistent diagram with the distance from each point, to the x equal y line. Okay, so this is the most persistent two-dimensional feature in our diagram, is the class number 6 in our two-dimensional barcode. Let's try to plot it, okay? And here it is. You can see that now I have a 2-cycle, so a sum of two-dimensional simplices. Each of these is a triangle. And you can see that, okay, it is random data, so again, this is not very meaningful, but if you really want to see something, you can see that there is a little bit of void in this data, okay? There is, I mean, the density of points is a little bit lower in this, in the space enclosed by this surface spanned by the triangles, okay? This is what two-dimensional persistent homology is telling us about this data. You have a void in points in this position. We might want to do the same thing for dimension 1, and we can see that dimension 1 is even noisier than dimension 2. The barcode is made up by several different bars. Many of them are quite long, but there's nothing really, much longer than anything else, okay? Nevertheless, let's look at the biggest one. I'm always confused what's the class here, so let me plot the diagram in dimension 1. So let me pick this one. This seems to be the most persistent one-dimensional feature, is the number 30. So let me plot it. Now I'm interested in dimension 1, class number 30. And here it is. There is, even if you want, less significant than the two-dimensional one, but still kind of cool to see. Okay, so Irene and persistent homology is recognizing that there is kind of a loop there. Okay. As before, we can plot the barcode in dimension 1, for example, and we're going to have in this case a 30 times 2 array because I have 30 different one-dimensional feature. I can plot in dimension 2. Now I have 7. The second dimension is always 2 because remember, in the barcode we have encoded the birth time and the death time of the filtration of the homology classes. Okay. Alright, this is just to help those of you that are perhaps more familiar with Python like I am. If you want to find out the length of the barcode, so how many classes, you just use the function size, okay? And you are interested in the first dimension, the first size of the barcode, okay? In this case, 7. As before, I can plot the a specific representative. In this case, I'm trying a two-dimensional cycle. I'm picking the second one, and as I told you before, the output is an m times n array, where m is the dimension plus 1 of the cycle. In this case, the dimension is 2 and m is equal to 3. And this is because this cycle is spanned by 22 second dimension in the output, 2 simplices, so triangles, and each triangle is spanned by 3 vertices, okay? So you have to read this array as the list of all the simplices making my two-dimensional cycle. Each column is a simplex, okay? Just, you know, to be super sure that we are understanding, here is the first homology class in dimension 1. Okay, and in this case I have a 2 times 4 array, a cycle spanned by 4 one-dimensional simplices, and we can plot the result by using the write DLM function. Okay, and this is going to be saved, maybe let me show you. This is going to be saved as a text file. Okay, where is it? All right. Okay, and then you can read this file with any language you want. All right, now so far we haven't really been looking at, you know, meaningful data. So this is going to be the first example in which, you know, persistent homology is really literally going to tell us something about our point cloud, about our initial data. It's a synthetic example because we kind of already know what to expect, but still instructive to, you know, make sure that what persistent homology is telling us is what we want to know. Okay, in the cases in which we expect, we kind of know which result to expect. But checking that this algorithm gives us the expected result is a good reality check. Okay, so let me load this point cloud. As the name Noisy Torus suggests, I'm just sampling a bunch of points on the surface of a torus, so the surface of a donut. Remember when I was telling you about homology, we agreed that a torus has, as homology, has 2 distinct one-dimensional features because it has 2 distinct one-dimensional holes. One spanned by this curve here, and one spanned by the perpendicular curve. Okay, one spanned by this curve there. Okay, and we are hoping that persistent homology is going to recognize that these points come from the surface of a torus. Now, this point cloud is quite big. It has quite more points than the other ones we consider, and since we don't want to lose too much time in computation, I'm asking Irene to stop the filtration when the time parameter is bigger than 0.5, and as you can see from the figure, this is going to be more than enough because pairwise distances between points is very small compared to 0.5. Okay, so it's reasonable to expect, we're not sure of course, but it's reasonable to expect that nothing interesting is going to happen for time bigger than 0.5, okay, because the points are quite close between each other. And this is something, a feature of Irene that's very useful in applications, right? Because if you want to work with real data, you're going to have something messy, you're going to have many points in your point cloud, and you are going to be very interested in doing things fastly. All right, so we computed it. Let's plot the point cloud in dimension 1. I didn't compute dimension 2, okay? we stopped at dimension 1. And here it is. And as you can see from the point cloud, we should be already happy, right? Because we see that there's a lot of noise, lots of small bars, but we see 2 bars that are much bigger than the others. Okay? So we are hoping that these 2 bars are going to represent exactly the 2 different one-dimensional features of a torus, thus telling us that these points are likely to come from a surface, from a space that has the same topology, the same homology of a torus. Okay? All right, let's plot also the persistent diagram. Now, since this one-dimensional feature stays until the end of the filtration, I told you that Irene records it as dying at infinity, and in a persistent diagram this is shown by plotting the feature in red in the y = x-axis. Okay? So we see the 2 one-dimensional features that are much more important, much more persistent than the others. This point here, this isolated point here, and the dying at infinity one shown in red. Okay? And these are the number 679, and 678. Let's try to plot them and to see whether they really represent, what we expect. So let's plot the first one. And here it is. And indeed, we are very happy, right? Because this is exactly recognizing that persistent homology, this is exactly telling us that persistent homology is recognizing this one-dimensional feature of a torus, okay? And for the other one, all right, and here it is. And as well, I mean, a little bit noisier than the other, but still, this curve is spanning the other one-dimensional hole. Okay, so very happy about the result. We are detecting that this is a torus. Okay. We might decide that we want to look at this curve without, showing it on top of the point cloud, and perhaps we also want to get rid of the label just to have a nice picture of it. And here it is. Okay, very nice. This is one cycle representing the biggest one-dimensional feature in our point cloud. Now, from this example, perhaps you can appreciate also why this cycle representing homology classes are not unique. Indeed, maybe the picture is too messy, but you can imagine how, for example, going from this point here to that point there towards a different point, and this one would have given a cycle still representing the same feature. Okay, so they are not unique. There are several of them that can be taken as representatives. Irene makes a choice. Irene picks one. All right, let's look at a similar example. Again, generated data, so we know what to expect. In this case, I sampled a bunch of points in the surface of a sphere. Here it is. I want to see again if persistent homology is able to recognize that I'm sampling points on a sphere, if it's able to recognize that these points are part of a sphere. So let's compute it. And let's plot the barcode in dimension 1 and 2. Now dimension 2 is what I'm interested in, right? Because I kind of want to see that persistent homology detects a unique or a bigger, much bigger than everything else, two-dimensional feature. That's going to tell me that I'm working on a sphere. And here is the barcode in dimension, 1 and 2. As you can see, dimension 1 is quite noisy. There's nothing, no bar striking out from the rest, okay? So this tells me that perhaps there's nothing interesting happening at the one-dimensional level, okay? There's nothing that strikes as an important feature. In dimension 2 is quite the opposite. I have a big, big bar, okay? This is probably, likely, going to correspond to an important topological feature of my point cloud. Okay, this is the persistent diagram in dimension 1. Let's just check, okay, the most persistent one. For example, this one, the most persistent feature in my my diagram, just to check if it is something interesting or not. This is the class number 35, and let's plot it. And I mean, doesn't tell us much, okay? It just tells us that perhaps on one of the two sides of this cycle, points are maybe less, dense than the rest of the sphere. Let's look at the big two-dimensional feature we found. Let's plot it, and unsurprisingly, let's give it time, we'll see that indeed this is, it takes all of the points in the sphere, and it's showing us that it's showing us a triangulation of the sphere, okay? All right. Any questions so far? We are going to slightly change subject, and we are going to see perhaps one of the most common ways of using persistent homology, okay? Often persistent homology together with adding a distance on persistent diagram, adding a metric on persistent diagrams is used to cluster different point clouds, cluster different kind of data. So understanding what's similar and what's different from each other, okay? And we are going to do that in this example. I need a bunch of plotting function to do that, and before actually I see a question. I saw it for a second, but let me find the chat. Right. Yes. Not directly with Irene. No worries. Not directly with Irene. But there is a very recent. So it's a hard problem, okay? It's a very hard problem to find minimal cycle representatives. Indeed, is with I think with both integer and Z2 coefficients is NP-hard. However, you can find approximations to this problem. Okay, I'm going to share in the chat one paper, and then from there you can have an understanding of the literature. It's a very hard problem. There are ways. No way is perfect. Okay, let me quickly Google it. All right, it was faster than expected. Just give me a second. This is a very recent paper tackling this problem. It's a very well written paper. There are also YouTube videos from the first author, which I think was an undergrad while working on this research, so that was quite impressive. In this paper there are a few results on this problem of finding minimal representatives, and there's a very nice code implemented that builds on Irene. One of the authors, Greg, is the person behind Irene. So from there you can have, an idea of the state of the art on these problems, and also you'll have access to some of the implementations. All right, now am I receiving other messages? Oh, okay. You're very welcome. All right. Let's go on. Before looking at the actual example I want to show you, again, I want to repropose the small example that I showed you in class last time. I'm plotting now two made-up persistent diagrams superimposed to each other. We have the blue one, D1, and the orange one, D2. We can ask Irene to compute the Wasserstein distance between them. Remember that we have to specify two parameters for Wasserstein distance, and that roughly each one of these versions of the Wasserstein distance is going to find the best possible matchings between points in the first diagram and points in the second one, and then is going to compute the distance, pairwise distances using this matching, where the distance used is specified by P and Q. In this case, P and Q give us the Euclidean distance. It's clear from the picture that the best possible matching, in this case is the one associating this dot here to that, those two and those two. And if you do the math, you'll see that the sum of their pairwise distances is 1, plus 1 is 2, plus square root of 4, no, it doesn't. Do the math. Now I'm making a mess. Now I'm confused. I won't try to do the math, but do it. I encourage you to do it, and you'll see that this is the right answer. All right. Now let's look at something more interesting. Okay, something in which we will actually use the fact that these distances between diagrams correspond to distances between shapes, and we'll use it to cluster a bunch of data I generated. Let me load this data. And all right, so I am uploading a bunch of point clouds that span a bunch of different noisy circles. Okay. For each one of those, I can compute persistent homology. Let me just check that persistent homology is recognizing that we're working with circles. So as in the case, as it happened for the torus and the sphere, in this case we expect to see the homology features of the underlying, shape of my point cloud to appear in persistent diagrams and barcodes. In this case, I expect to see a bar, a one-dimensional feature, much bigger than the others. Okay, let's plot, and here we are. Okay, we have this persistent plot here. It's much more persistent than everything else. So Irene is recognizing that we are working with a circle. Now I am extending the data set to add several different versions of pair of disjoint circles, pair of adjacent circles, and pairs of concentric circles. Let me just plot them. So this is my entire data set. I have 4 noisy circles, 4 noisy concentric circles, 4 noisy adjacent circles, and 4 disjoint circles. Okay. I'm hoping to be able, using persistent homology, to distinguish the 4 groups. Okay. Let's pick one specific example, one specific disjoint circle, and let's compute persistent homology just to have an idea of what's happening, what persistent homology is going to tell us. And here we are. Okay, so we are kind of happy because we are seeing two features much more persistent than everything else. So I have a bunch of noise here close to the diagonal. Perhaps this works better. So I have a bunch of noise, a bunch of one-dimensional features with very low persistence, and then I have two classes with a very big persistence compared with the rest. Okay, and these I'm hoping I'm hoping they will correspond to these two cycles. All right, so let's plot them. One is this one, and I'm quite happy. Let's look at the other, and very happy as well. Okay, Irene is exactly detecting the two one-dimensional features of my point cloud. Okay. What I want to do now is compute persistent homology of all these point clouds. I have 20 of them, 5 for each type. I want to compute all the persistent homologies, and then I want to compute pairwise Wasserstein distance, hoping that I will distinguish the 4 groups. Okay, perhaps before we do that, we could try and have a look at one of the concentric examples. For example, I can pick the third one. Okay, let's look at this example here. Let's compute pH. Just to make sure that, again, we are kind of doing what we want, okay? Okay, so something different is happening than before. Okay, I still see two more important classes, but the second one is not so different from the noisy ones. Okay, and this is bad news and good news. Good news because still persistent homology is recognizing that I have two loops somehow, even if the overall picture is much less. If you want the resolution, if you want, is much lower than before. So good and bad, but also I'm hoping that this will allow me to, recognize the case of concentric circles from the case of disjoint circles. Okay, because in the disjoint case I had two very, very high, very persistent features. In this case, I have one very persistent and one kind of in the middle, together with all of the noise. Okay, let's just plot these. What did I do? Let's just plot these two cycles to see what they tell us. And these are the number 24 and 23. Let's look at them. First circle, the inner one, and 23. And the outer. Oh, you see something weird is happening. This is not the outer one. This is the sum of the outer and the inner. Good example that shows you that the choice made by Irene is not necessarily the best one. Okay. The overall information from an homological point of view is still the same, because persistent homology is telling us that most of the homology, most of the features are given by these two cycles. One is these two, made up by these two, and one is this one. Okay. Overall, they give us the same information if you consider them together, but the choice of the cycle representing the second class is perhaps not the optimal one for interpretation. Okay, we would have preferred something not including this one. Okay. All right. Anyways, we are kind of hopeful that computing persistent homology of everything and then computing pairwise distances is going to tell us something. I just want, you didn't even notice perhaps, I'm just computing persistent homology in fractions of seconds for all of these point clouds. So it is very fast, okay? It's a neat object, persistent homology, because it tells you lots of information about data in a very computationally efficient way. Especially this iron package is very fast, performs very well. Here I'm just computing a bunch of pairwise distances as examples, but let's not look into that since we are kind of late, and let's just compute the pairwise distance matrix. Okay, I'm creating this M as the zero matrix of size 20 times 20, and then I'm computing pairwise distances between all the persistent homologies of all my all the point clouds in my data set. Let's compute it. Already done. This is my pairwise distance matrix, and let me plot it. Okay. Now I have first this square here correspond to the single noisy circles. This square here correspond to the concentric ones. Then I have, I think, the I don't remember the order actually. Then I have the adjacent and then the disjoint. Okay. Now I think we can say that we are half happy about this result, because I think it's we have a clear separation between the group made up by single and concentric circles, and then the group made up by adjacent and disjoint circles. Then, if we close up in the first group, I think we can clearly separate the noisy circles from concentric ones. The single circles form a very dark square, so they're clearly separated from the concentric ones. However, we can't really distinguish things here. Okay, we really can't. And if you think about it, we should have expected that, because the only difference in the shape between the two classes of data sets was the fact that the circles are either attached, adjacent to each other, or separated. Okay, and that's not much. At least it's not much if you want to use first homology. But perhaps we can use zero-dimensional homology that's most interested in connected components, and maybe using that we will be able to distinguish them. So let's try that. I'm doing exactly the same thing, but now I'm looking at the barcodes in dimension 0. Now this is going to take a while. Why? Because the barcodes in dimension 0 are much bigger than the barcodes in dimension 1, right? Because for each of the point clouds I have one feature in each for each point. Okay, so I don't remember what was the size of the point clouds, but in the order of a couple of hundreds. So I have bigger arrays to compare to each other, so it's going to take a little bit longer. Not much, as you can see, it's quite fast, but we'll have a few seconds to chat. Okay, let me compile this stuff as well, so when it's done. What did I do? Okay, when it's done, we're going to have the plot. In the meantime, if you have questions, this is a good time to ask them, either in the chat. I have eyes on it now, or yes.
Hi, do you know if we'll be able to have some recordings of the lectures?
We will be able to have recordings of the lectures, and we will post them on the TDA Center webpage, and we will advertise it when we do. if you don't hear anything in a few weeks, just send an email to either myself, Oliver, the other lecturer, or Heather that organized this, and we will get back to you. In the meantime, I'm happy to share the slides, and you can, if you are taking part in this course, at some point you should have received the invitation or the advertisement in a PDF. You can download all the materials they used today from a link contained in that PDF. If you can't find it, send me an email. And if you want the slides, send me an email. All right, we are done. I didn't even notice. And here is the heat map, and okay, we can separate everything, okay? Because zero homology, it might be, it's much less interesting in most of the situations, but sometimes it's what does the trick. That's it for today. Is there any other question, either about lectures or today's computations?
I'm sorry. Could you please say again how to distinguish actually things via the heat map?
So this is showing the pairwise distance matrices, okay, and colors correspond to value of pairwise distances, and the elements are ordered in the following way. First, I have the 5 pairwise distances between the 5 point clouds corresponding to noisy circles, this square here. Then I have the 5 concentric circles, so these diagonal square would be pairwise distances between the concentric circles, and these 2 squares here would be distances between each point here is distance between 1 noisy circle and 1 concentric one, same thing on the other square. And similarly, this square here correspond to pairwise distances between adjacent circles, and these by these joint circles, or vice versa. I don't remember the ordering. And you see that since the squares are visible, that means that pairwise distances in each of the groups is smaller than pairwise distances between elements in distinct groups. Okay, and that tells us that 2 point clouds are more likely to have similar persistent homology if they are part of the same class. In other words, by computing persistent homology, we are able to distinguish these 4 shapes of circles. Does it answer your question?
Yes, thank you very much.
You're very much welcome. Is there any other question? Yes?
How can we represent this with a new version of Julia?
Can you say it again? Sorry.
Yeah. We are not. How can we do the plots in a new version of Julia instead of the old one that we are using?
So there's like this package here that I'm not super familiar with. Plots. It's called just Plots, and it's similar to Plotly, and I'm sure you can plot heat maps there. Well, to be honest, what I do is that I perform analysis on Julia, and then I do everything. Then I save things, and I do everything on Python. Mainly because I do like Plotly very much, and I kind of want to keep using it. So I just do the analysis on Python. What I do for practical purposes usually is when I have a point cloud, I compute persistent homology with Irene, and then I save a dictionary with 2 entries. First entry is the barcode, it's just an array, and second entry is an array of arrays. Each element in this array is the cycle representative chosen by Irene, and they are in the same order, okay, as the barcode. So I have one array giving me all the fixed dimension. Okay, say that we are interested in dimension 1. I compute pH in dimension 1. I create the dictionary. First key in the dictionary is barcode. Element of barcode is a two-dimensional array, so an array of length something with 2 entries in each, a 2 array in each entry, birth and that. And then I have a list of arrays ordered in the same way as a barcode. Each entry in this array is the list of simplices representing the feature. Okay, and that's everything you need, right? If I want to compute Wasserstein distances, then I do that in array, and then I just save the matrix. Okay. This might be a good time to advertise Catherine. She's a student here in Oxford, and for a joint paper with me and Heather, she Pythonized a bunch of I see there's a comment. Oh, great. Thank you for sharing that. And if you want to have something more Python-based, you can have a look at this GitHub by Kate. This is the code we use for our paper in which we computed persistent homology for knotted proteins, and we said we were able to say things about them from a structure point of view and from a low-dimensional topology point of view as well. She wrote this very clean, very user-friendly code. She computes landscapes as well, and then she has implementations for distances within landscapes and plotting things. So it's very clean, very well done. So I would encourage you to have a look there. It's in the chat. All right. If there's no other question, I will call it a day, and I want to thank you very much for participating in the course. Maybe, Oliver, you want to say thank you and say bye to people online as well, since you are in the audience.
Thank you, everyone, for attending the course, and yeah, we'll let you know about the recordings. And also, feel free to email me if you want the slides from the second lecture.
All right, bye-bye. Nice seeing you all. Bye-bye.
Thank you. Bye.
Bye. Thank you as well, and sorry for not making eye contact, and sorry for all, taking a huge amount of time to do everything today. I really